Swayam Prabha. Digital India. Educated India.
Hello, we continue our lectures on variational methods in mechanics and design, and today we are going to take a small detour from calculus of variations. As we have discussed in the last 3 lectures, calculus of variations is crucial for variational methods, whether it is applied to mechanics or design. And calculus of variations, as we have discussed, is an optimization problem where the function itself is an unknown, but finite variable optimization is different in that there are finite number of optimization variables x1, x2, xn and so forth. Okay. So, today we take a small detour to talk about finite variable constrained minimization, that is, it is an optimization problem without any constraints. We just have an objective function that we minimize with respect to finite number of variables, meaning there are x1, x2, x3 and so forth up to xn, where n can be just one variable, n can be two variables, n can be any number, but finite number. For such a problem, we will discuss today necessary and sufficient conditions for finite variable unconstrained minimization. Here is the outline of the lecture. We will start discussing the necessary conditions and sufficient conditions for a problem with only one variable, and then move up to 2 variables and then jump to multiple variables. There can be n, where n can be any number, it can be 100, 1000, 100,000, does not matter. We will discuss necessary and sufficient conditions for such a problem. First, what we will learn will be the concept of a local minimum, which is very important for optimization. It is only a local minimum that we have control over in terms of how we find it. There is also the concept of global minimum. We will discuss the difference between the two, and then we will also discuss what is the basis, what the basis is for writing the necessary conditions, and then for that we need the concept of a gradient and also something called a Hessian for sufficient conditions. So, let us look at a very simple case of a problem which is stated here, just f of x. Okay. So, we have this function f of x, a function in one variable x, okay, a single variable x that we have. For such a function, if you think about a minimum, we want to have definitions first. What we call a minimum? There are 2 kinds of minimum as indicated here, global minimum and then there is local minimum. Okay. Global minimum is defined as it is shown here. If for f of x star, if x star is a global minimizer, meaning that x star is a particular value at which point this function f of x has the largest value. When you say global minimum, largest value that satisfies this definition, that is, its x star is a global minimizer of f of x if this condition is satisfied for all x. This symbol, as you know, this symbol stands for all. Okay. So, for all values of x, f of x star is less than or equal to f of x. That is, you have some domain for the function f of x. In that domain, whatever value you take for x, then f of x star will be smaller than f of x, smaller than or equal to, less than or equal to. Such a minimizing point x star will be called a global minimizer. That is clear. So, if we say that you have the smallest weight in a group of people, then your weight should be smaller than everybody else's weight, then your weight will be a global minimum. right. As opposed to that, local minimum is defined differently. As you can see the second line here, x star is a local minimizer of f of x if similar condition we have f of x star is less than or equal to f of x, but this is not for all x in the domain, but only in a small neighborhood of x star in the feasible interval of x. So, x has some values that are permissible, what we call feasible values, but then we are not taking all the values. All we are saying is that x star has a neighborhood that we can define. In that neighborhood, in that local neighborhood, that should be the lowest value. Okay. So, if you instead of think of a minimum, if you think of a maximum, let us say you are a school topper, you are a local maximum, because compared to the other students in your class, you are the topper, right. But then if you consider the entire state or entire country or world, if you are still higher than any other student of your age or your class, there will be a global maximum. So, global maximum, global minimum has exactly that thing. In a local minimum or maximum, we have to look at a small neighborhood, that is around you, you take a small neighborhood, you and your class, then it will be a local best, local minimum. If you are the best in the largest group that is there, then you will be global minimum or a global best, okay, global optimum. Okay. Let us understand these two definitions first. These are the definitions, and definitions are well, before we go to that, let us see this small neighborhood, let us actually define that also. Okay. Small neighborhood, it is that neighborhood x where x belongs to some set S, okay, with this condition satisfied. So, we have defined this delta, which is a small positive value, x minus x star. So, we are talking about neighborhood around x star, right. So, the distance between x star and any other point x you take, okay, that is why we take this as, later on we will call it a norm, but right now think of it as a distance. Distance from x star to any other value, if it is less than delta, that will constitute the small neighborhood around x star. Okay. Let us understand this figuratively, okay, or using a figure. So, if I have a one variable problem, okay, let us say I am like this, and somewhere here, so let us say the x goes like this, there are a lot of different values of x. Now, let us say there is a particular point which we call x star, all right. Now, for this one dimensional problem, single variable problem, I can define a small neighborhood, okay, small neighborhood. So, that I can say is from here to here around our point x star, I can say this is 2 times some delta, okay, that is delta on the right side, delta on the left side, that is the small neighborhood. In that neighborhood, if this x star has the least value, that we call a local minimum. Okay. If we go back to the definition here, that is exactly what we are saying, the small neighborhood. Now, instead of taking a single variable, let us take two variable problem. Let us say I have two variables x1 and x2. Now, I take a particular point, let us say this is x1 star and this is x2 star. Okay. So, these coordinates are x1 star, x2 star, then I can define a small disk around it, okay, of radius, for that radius equal to delta. Okay. Here it was a small line, that was the neighborhood there, but here we have this whole disk as the neighborhood. Within that neighborhood around x star here has two values, it is a vector now, x1 star, x2 star, two values. Around that, if we define a disk of radius delta, which is positive, which is greater than 0, right. In that neighborhood, if this has the lowest value, we call that a local minimum. Now, if I take 3 dimensions, okay, let us say I have x1, x2 and x3. Okay. Now, I have a point somewhere which has coordinates x1 star, x2 star, x3 stars, then I can define, it was just a little one dimensional domain, two dimensional it became a disk, in 3 dimensions it will be a ball. Okay. Now, this is a ball of radius delta again, small neighborhood. So, we are just defining our small neighborhood around our putative optimum x star. Okay. I will put a bar, so it can be x1 x2 or x1 x2 x3 like a vector, that is a small neighborhood. Okay. Within that small neighborhood, if you have this point to have the least value, then it is a local minimum. Otherwise, if it is for the entire domain, if it is the lowest, then it is called a global minimum, and that is exactly what these two definitions tell us. Okay. So, these definitions are good, but they are not practically useful. Okay. Somebody gives you a problem and says, okay, here is a local minimum or here is a global minimum, right. How will you check? You cannot check this entire neighborhood, right. For example, you claim you go to your house and say I am the school topper, then your neighbors have to verify that, they have to come to the school and ask marks of every one of our classmates. So, they have to make sure that everybody is asked, which is very difficult. If it is a large school, if you say I am the country first, then I have to ask every kid of your age to ask how many marks they got, right, in order to confirm that you are the topper. Similarly, here if you say this point is a local minimum, then you have to check around this neighborhood, exhaustively search and find, which is not practical. So, definitions are not enough, we need conditions. So, we have a condition, you plug some values into it and then verify it is a local minimum or a local maximum or global minimum, global maximum. Let us see if such conditions exist. Okay. Pictorially, let us first see how they look like, right. So, here we are showing a point which is a global minimum that we have indicated, right. This point is a global minimum, because in the domain that I have shown, let us say domain from here to here of this x here, this is a global minimum because that is the least value, every value is above it, right. According to our definition, the global minimum is that. But you look at this point, that point is a local minimum, meaning that in the small vicinity, if I take, right, it is a one dimensional problem, in that small vicinity of x here, that is the least value, locally it is the least value. Okay. Similarly, one can talk about global maximum and one can talk about something called a inflection point or a saddle point. Sometimes we call it saddle point, sometimes we call it inflection point. Okay. Here looking this side, it is a local maximum, that is looking at coming from this side, it is local maximum, coming from this side it is a local minimum, right. Such a thing as inflection point, where it has a special thing that when you draw a tangent, the curve is on both sides, whereas if you draw a tangent here, curve is only one side above for a minimum or local minimum, global minimum. If it is a tangent here for a maximum, the curve is below the point, okay, where the tangent is, right. So, these are the graphically the concept of a local minimum, local maximum, global minimum. I can have a global maximum also in a problem, right. Now, definitions we have learnt, graphically we understood what they are. Now, let us find conditions. For a one variable problem, it is very simple. All we say is that if x star is a local minimum, such conditions which are operationally useful can be written for local minima, but not for global minimum. Okay. Plural of minimum is minima, do not say minimums, that will be incorrect grammatically. Minima, multiple local minima. Okay. So, global minimum there will be one, local minima there can be several. For every one of those, if x star is a local minimizing point, then the condition that it should satisfy is written here. Okay. It says df by dx, that is the derivative of f with respect to x, is equal to 0 when it is evaluated at x star. Okay. That is clear from this graph. So, tangent df by dx is the slope at this point is 0. Okay. Slope at this point is 0. If I take a point like this is not a local minimum or local maximum, because slope at that point is not 0, right, or this point not 0, slope at that point, whereas here slope is 0, but it is neither a minimum nor a maximum, or it is both. Okay. But in any case, the local minimum has a condition that slope at that point is equal to 0. Okay. That is a necessary condition. The slope being equal to 0 at a point is a necessary condition for that point to be a local minimizer. We have a necessary condition, we also have sufficient condition. If there is such a point which satisfies the necessary condition, that is df by dx at x star equal to 0, then if this is true, that is d square f by dx square evaluated at x star, if that is greater than 0, that is sufficient. Okay. So, now we have necessary condition and then sufficient condition. Okay. These are conditions. So, if somebody gives you a function and gives a value and say that this function has a local minimum at that point, then immediately you take derivative, substitute that value, that x star that is given to you. If the derivative is equal to 0, then you can say yes, your point could be a minimum because it has a necessary condition. And then you find the second derivative d square f by dx square. If that is greater than 0 at that point, you say it satisfies sufficient condition. So, necessary sufficient both are satisfied, then you say okay, what you have given me is a local minimum, right. So, here you just need to substitute into the derivative, first derivative and second derivative at that value, and you are done, unlike exhaustively searching the entire space, entire domain of the function. Okay. That is why conditions are useful operationally as opposed to definitions. Definitions are important to understand the concept, conditions are important to solve problems. Okay. Now, we have defined two words, necessary and sufficient. You have to say, why is the necessary condition not sufficient? There are two different words, right. We say condition is necessary, we are not saying necessary condition is sufficient, and we are saying sufficient condition, why is it not necessary? Okay. Let us look at these two terms. Necessary condition is not sufficient, sufficient condition is not necessary. Okay. They are two different words. While these words necessary and sufficient are very simple words in English language, in mathematical sense for optimization we have to understand their meaning. In fact, they do not suggest anything other than what they actually say. Necessary means it is necessary, it is essential, it is necessary, and sufficient means it is adequate, it is sufficient. They do not say anything more, but we should not get confused. Okay. So, let us ask this question, why is the necessary condition necessary first, and then we will say why is it not sufficient. First let us understand necessary condition being necessary. So, for that let us consider Taylor series expansion of the function f of x around this point x star. So, that we will say this necessary condition is actually necessary. Okay. How do we do the Taylor series? If you remember, so we have, if I want to expand the function f of x around a value x star. Okay. So, f of x star we know the value of the function. Using that information we would like to approximate the function or expand the function, not approximate, put equal to now. So, I will have several terms, right. First term what we call 0th order term, and then we will take the derivative of this f at derivative with respect to x and evaluate it at the point around which we are expanding, and then multiply by the distance of that x from x star. Okay. and then this is the 0th order term, this is 0th order term, okay. This is 0th order term, this is the 0th order, okay, and this is first order. There is second order also, where you take derivative with respect to x twice, evaluate at x star, and then there will be square of this distance x minus x star square, and there will be more and more. So, this thing is second order, third order, and so forth. If you write up to nth order as many times as you want, your function will be more and more closer to what it will be for f of x. So, x minus x star should be small. If you say I know the value of f at x star, if you want to estimate for f of x, if you know the first derivative and second derivative, you will get some approximation. We call it first order approximation, means that if only up to this point you take, that is a first order approximation. If you take up to this, we will call second order approximation, and so forth. That is, you are approximating the value of the function using the derivatives of the function at a given point. Okay. This is Taylor series, which you all know. There is also remainder form, which we do not need right now. Okay. So, this is what we just wrote in the previous slide, right. There is 0th order term. So, we are perturbing around this x star delta x. So, whatever that we have x minus x star, we can call it delta x star as it is indicated there. Okay. Then we have the 0th order term, which is in blue color, and then we have first order term, which is in red color, and then there is second order term, which is in this magenta color. And then there are higher order terms, O3, that is how we write, that is order 3 and higher. You can have third order, fourth order, fifth order, you take as many derivatives also when you do that. Okay. Now, if you look at this, let us ask the question, why is that necessary condition? We said df by dx at x star should be equal to 0 is the necessary condition, that is, this thing over here should be 0 for the necessary condition. Why is that? We said for a local minimum x star in the neighborhood is defined by this delta x star. Okay. This delta x star that we have, that is our neighborhood, right, x minus x star. If I keep this, what we called delta earlier, if I keep it around that point x star, okay, and I can make this as small as we can imagine. So, this one you imagine as small as possible, as small as you or one can imagine, okay, very small. In that small neighborhood, we want f of x to be larger than f of x star, or rather f of x star should be smaller than f of x, right. If you look at that, let us say we make this delta very small, very small, so small that all of these, okay, second, third, everything can be assumed to be 0, because second order term will have x minus x star square, third order will have x minus x star cube, and so forth. If delta is very small, as small as you can imagine, right. So, if it is very small, then you can neglect all of them, then it boils down to only the first order term. This is 0th order, it will be a numerical value once f is known and x star is known, this is a numerical value. This is the one that varies as we make this delta assume smaller and smaller values. Then it will all depend on this first order term, right. Now, we do not know the sign of df by dx at that point x star, it can be positive or negative. Let us say it is positive. It is positive and x minus x star is also positive, then f of x will be, this is positive, it is fine, f of x is larger than f of x star. But what if I take x minus x star or this delta to be negative, right, then f of x will be smaller than f of x star, because it will become f of x star minus this value which I assume to be positive, this will assume to be positive, and if this value is negative, then overall its negative value, function value will be smaller for some other point x as compared to f of x star. That is not allowed, because we said x star is a local minimum. So, because this term, that is this term, can be positive or negative, we want this to be equal to 0. So, to first order the function value does not change. If it is 0, the first order term goes to 0, right. So, as you make delta smaller and smaller, this f of x will not be different from f of x star. Okay. That is a necessary condition. Without that we cannot say, because we are imagining delta to be as small as one can, we want the first order term to go to 0. Okay. There are rigorous proofs for this, but this intuitive proof is good enough for this detour that we are taking. Okay. So, that is why necessary condition is necessary. All right. So, okay. So, let me erase some of it, or okay, it is okay, I will explain what I have written over. So, it is just that some notation is there. Okay. So, let us go to the next one and then talk about notation. So, this thing here f prime is first derivative df by dx. So, when I write f prime, what I mean is df by dx. Similarly, we have f double prime, okay, that is second derivative d square f by dx square. Okay. F of x equal to f of x star, 0th order term, first order term, 0th order term, first order term, and then second order term and higher order terms, right. So, now whatever I said, this may be positive or negative depending on the sign of f x star, sign of f prime here, f prime x star, that can be positive or negative, right. Hence, we say that should be equal to 0, that is the necessary. If you want to have f x star less than or equal to f of x, is necessary to have that equal to 0. Okay. That is our condition. Now, why is the necessary condition not sufficient? Okay. Now, we said in the small neighborhood it should be a minimum, and hence the first order term should be 0, right. First order term is 0 for a minimum as well as for a maximum, which we know that slope is equal to 0 for a minimum, local minimum as well as local maximum. In that sense, necessary condition is not sufficient for a point to be local minimum, okay, because both maximum and minimum satisfy the same condition. Okay. Now, we also said sufficient condition. What was sufficient condition? Sufficient condition is in our notation now, f double prime x star should be greater than 0. When I say x star, that automatically means that df by dx evaluated at x star is equal to 0. Okay. At that point we want it to be greater than 0, right. Now, this is a sufficient condition, right, that is a sufficient condition. That sufficient condition is not necessary, that should be greater than 0 is not necessary. We can understand that with a simple example. So, consider this f of x to be x raised to 4. Now, f prime x is 4x cube, right, take derivative with respect to x. Now, according to necessary condition that should be 0. So, 4x cube equal to 0 gives you that x to be 0. So, that is our x star. Now, consider second derivative f double prime, which is 12x square. Substitute x star equal to 0 there, you get 0, right. It is not greater than 0, right, but look at this thing here, all right. This has definitely local minimum over there, right, yet our sufficient condition is not satisfied, right. So, sufficient condition now we say is not necessary, it is sufficient when it is satisfied, but it is not always needed, okay. So, it is not necessary. Now, for this problem we will take third derivative, which is 24x, that is equal to 0, also gives you x star equal to 0. You take fourth derivative, that is 24, that is positive. So, you have to go for the pair of odd and even derivatives, where even derivative is not 0, to conclude whether it is a minimum or a maximum or that inflection point. Okay. Anyway, with this argument we have understood necessary condition is not sufficient because that can be maximum or a minimum or inflection point. Likewise, sufficient condition is not necessary based on this example. All of these can be rigorously proved, but here we are getting an intuitive understanding because it is a detour that we are taking, right. So, now we have to understand the terms which simply mean what they imply in English, necessary and sufficient, but we should not be confused about these two terms. We should be really clear, necessary is absolute necessary, sufficient is just sufficient. Okay. Now, from definitions we went to operationally useful definition or a condition, right. So, given a minimum minimizing point and a function, we can verify now by substituting. At the same time we can also solve for it. Okay. We will solve this numerical example when we continue in the next lecture. Okay. Thank you.